One important property of the Laplace transform is called the final value theorem. And it's exactly what it says. It's the final value of a time signal that is described with a differential equation. So you have a differential equation with an input signal, and you would like to know what the output signal is after a long period of time. So this is called the stationary signal at the end, or the final value. So as this is y of t as t goes towards infinity. And the final value theorem says the following: we can compute this final value if we know the Laplace transform of the signal and let s go to 0. So this, you can imagine that this is incredibly useful because this is very difficult to compute with the differential equation. This is very difficult, very easy to compute if we have y given as a function of s. And if we look at an example, we had C1 delta of S, and this was defined with the delta input of 1.25 divided by 2s plus 1. So the question is, what happens if we spike the signal, our system, our concentration, what happens to it after all the disturbances have died away? And we find out that this is according to the final value theorem. So we get limit of C1 delta of t as t goes to infinity is equals to limit of s goes to 0, s times the Laplace transform of Ci, which is 1.25 divided by 2s plus 1. And so this goes to 0 because s goes to 0. This goes to 1.25, and 1.25 times 0 is 0. So that means, if you remember, we had the spiked signal, and so with the delta pulse, it went up to a value and then went down, and it stayed at 0. So now we can think about the same system if we entering a pulse. So here the input was a delta pulse, but what happens if we don't enter a pulse, but we enter a step function? So we can figure that out because C1 delta of S was 1 divided by 2s plus 1 times Ci of S. So our question is, if this Ci of S is a step, or the Ci of t is a step, then the Laplace transform of a step is 1 over s. So that's a unit step. So we're stepping it up with a concentration of 1. So that means Ci of t would have been a step, s of t. And we can stick this in there. So I have to just get rid of this. This looks so ugly. So we can answer the question, what does, and now also I made another mistake here. This is obviously not a delta pulse, but this is if we have a step function as an input. So we would like to know what is C1s of t. And we would like to know what happens as time goes to infinity. And we can answer the question using the final value theorem, because this is the limit times s times y of s. And now this becomes the transfer function. This is g1 of s times Ci of s. So this is our y of s. Sorry, this I should have written here C1s of s. And this is now s limit of s goes to 0. S comes from here. The transfer function is 1 over 2s plus 1. And our Ci of s is 1 over s. And these two s's now cancel out, and we are left with the limit of s goes to 0, 1 over 2s plus 1, and this is equals to 1. So this means that the first order process, if we are put in a step, will also go up to will follow the step, considering that we have a process gain of 1. So we have a number 1 here in here. This would be a different number, then it would go to the equivalent. So if would be a 2, the process gain, then our final value would go up to 2. So you can see how useful it is. And in fact, we can write something else. We can say limit of t goes to infinity, y for a step input of t is equal to limit of s goes to 0, g of s. So this means, because this always happens, this cancelling out of here, the cancelling out of s and 1 over s always happens. So we can do a shortcut and say if we have a step function and we would like to know the output using the step input, is simply the transfer function. So we're getting two very important equations here, this one here and this one down here, and they are incredibly useful throughout.